What is critical opalescence in thermodynamics? Imagine looking at a glass of water that suddenly turns milky and cloudy even though it's still transparent. That's a glimpse of what happens during critical opalescence, a fascinating phenomenon in thermodynamics. It occurs near the critical point of a substance, where the boundary between liquid and gas phases blurs away. At this specific temperature and pressure, called the critical point, the densities of the liquid and vapor phases become equal, forming a single supercritical fluid. As the system approaches this point, tiny fluctuations in density start to grow. These fluctuations happen on a microscopic level but can become quite large. When they reach sizes similar to the wavelength of visible light, they scatter light strongly. This scattering causes the fluid to look milky, cloudy, or opalescent, even though both the liquid and vapor parts are clear on their own. This is what we call critical opalescence. From a thermodynamics perspective, critical opalescence signals a second-order phase transition. During this transition, the latent heat of vaporization, or the energy needed to change from liquid to gas, drops to zero. The fluid becomes highly responsive to small changes in temperature or pressure, leading to these large-scale molecular fluctuations. These fluctuations cause variations in the refractive index and density, which are responsible for scattering light. Understanding this phenomenon is important in the field of mechanical engineering, especially when dealing with supercritical fluids. These fluids are used in processes like extraction, chemical reactions, and heat transfer because of their unique properties. Recognizing the behavior near the critical point, including critical opalescence, helps engineers design equipment that can operate safely and efficiently under extreme conditions. To sum up, critical opalescence is a visual sign that a substance is near its critical point. It shows how the fluid's properties change dramatically during phase transitions, with large density fluctuations causing the milky appearance. This phenomenon is a key part of understanding how fluids behave at high temperatures and pressures, especially in advanced engineering applications.